See, yesterday we started off with system. First we should know what is signal. Now we know that it's a function of one or more independent variables. So it's a kind of mapping from of independent to dependent variable, right? So variable or variables, so mathematically it's a function of one or more independent variables. Well, systems, what we know is like, it's a kind of, we can imagine that as a kind of black box which takes the input signal and gives some output signal y of t. I'm assuming it to be continuous time. So it's a, this is in general a mapping, this is in general a mapping. So it's a mapping to mapping. Okay, it's a so physically it is some meaningful interconnection of some components. All right. So after that we have seen some system properties. We saw that many different systems physically, okay, they in general mean the same. We saw an example of a mass which has been given some force and it it accelerates. The relationship between the mass and the acceleration, and this is nothing but the acceleration, and we saw that there is a component of friction also present there. Or if you simply ignore that, this is in general equivalent to a capacitor current equation, right? So what is that? IC of t C dVt by dt. So there is a lot of similarity between these equations. In fact, they are the same. Only the variable inspection or the abstraction, I mean what I'm saying is abstraction remains the same, the variable or the context changes. So we saw some important properties of such systems. We started off with which property? Yeah, memoryless, memory systems with memory and systems without memory. Okay, then yes, causality, right? We saw the causality. What was that? Yes, so memory is something which is dependent on only current instances. Causality is something when the output is dependent on only present and the previous inputs, previous or past inputs, right? So, but if it is anticipative, that means if it predicts the future value, it is non-causal. Okay, so causal systems are non-anticipative. It doesn't predict any future. All right. Later we saw some more interesting properties. What was that? Stability. We saw that there are various variants of stability. Okay, but we were we restricted ourselves to what is called as a BIBO stability. Okay, of bounded input, bounded output stability. What is bounded? What do you mean by when I say a signal is bounded? What do I mean? The amplitude, yes, the magnitude of the amplitude of the signal, okay, is well within the range, right? It's finite. So that means the magnitude of that signal is having some real finite value, of course less than infinite. All right, that is what we have seen so far. We have seen a couple of examples in that regard, and later on, that's all we have seen last time. Yes. So let's begin with some more interesting properties. So another important property is the fourth one, right? Time invariance. See, a system is said to be time invariance if, say for example, if I'm taking some input and it produces some output, let's say y of t. If I shift that input or if I delay that input by some amount, let's say t naught, and assume that if the output also gets shifted by the same amount t naught, if this is true for all the values of input and all the values of t, I mean for all the values of t naught, all the shifts, then this system is said to be time invariant. Time invariant. and of course this should be valid for all t, okay, for all the time. Always remember, you need to check the input output relationship for all the values of time, okay, always remember that. Check the input, yes, see, what does this mean mathematically? I mean, see, physically what it means, suppose you are performing any experiment in the lab, some RC circuit or doing anything, you are getting some output. If you perform that experiment tomorrow or the next day, you should expect the same output, right? Of course, what is the difference? If the input is shifted or a delayed, that means you are giving the input the next day. The output also you will be able to see the next day. But there should not be any other difference without. If that is true, then the system is said to be time invariance, and this should be true for all the inputs and for all the time sheets. Say for example, you are performing the same experiment after a couple of weeks, it should still give the same output just by a delay of a couple of weeks. Just that there should be only time shift in the output, and it should be the same time shift by which the input has been shifted. Are you getting? So if the input is shifted by some amount t naught, the output must also be getting shifted by t naught. If that is the case for all x, for all t naught and for all the time, then we say that the system is time invariant, otherwise not. Take this example. Now things will be clear with this example. Yes, quick. Well, I'll come to that. Not necessarily. Let's see. Take this example. Y of t equal to t into x of t. Is this system memoryless? Yesterday we saw this, right? Is the current output dependent on only the current input? Yes. Check the current input. If it is only at t, it is not dependent on the future values of t. So it is, or the past values of t. So it's memoryless. Is it causal? Huh? Is it causal? Are you are asking the same question again and again. See, this should be true for all x and for all t. Is it causal? It is causal. Yes, confidently you should say that it's a causal. Now, is it time invariant? Let's see. Okay, let's see. So for time invariance, what do? We take the original input. If x of t, it produces what? T into x of t. So this is what, the original input. If we shift the input, shifting the input by t naught, what does it give? X of t minus t naught. That will produce, there is shift in the input, right? There is a shift in the input. What will happen? T x of t naught. We have shifted the input. Now we need to see if the output also gets shifted by the same amount. So let's shift the output. So let's shift the output by t naught, same amount. So what is that? If y gets shifted t minus t naught, what is this? The variable itself is getting changed, right? So every t is getting replaced by t minus t naught. So what it will be? T minus t naught into x of t minus t. Are they the same? No. That's why this system is not time invariant. Not time invariant. What is time varying? Is it clear? Your doubt is clear, Karthik? So the shift in the input should give the same shift in the output. So what we have done, we have initially shifted the input, tested what output could be, then we have shifted the output itself and check if both are the same or not. If it is not, then it's not a, it's time varying, and if it's the same, it's time invariant. Is that clear? And this should be true for what? For all shifts and for all x. Let's take some more examples. Consider this system. Y of t is to x of sine t. Or I'll take the other way around. Now this may be some complex, so I'll take some simple cases. Let's take sine of x. Both those two signals are not the same, right? Well, is this system time invariant? Shift the input. Go step by step. Initial input x of t will produce the output sine of x of t. If the input is shifted, so shifting the input will give t minus t naught, producing the output what? Sine of x of t minus t naught. Shifting the output इसको शिफ्ट करना है ना, y of t को y of t minus t naught. That means what? Wherever there is t, you replace it by t minus t naught. So it will be sine x of t minus. Are they the same? Yes. Same. So this is yes. It is time invariant. You can try the other example. Next, let's take some more examples. Take this. Tell me. Now solve this. Solve this by yourself. Always remember the definition. What is the definition? First, shift the input. By what amount? By some amount. Let's say t naught. Right? Try by using. Yeah. So what is the thing? Time variation. Time. Time. Time invariant. Time invariant. Time varying. Okay. So let's see this. This is interesting, right? So let's see this. That's why you have to be very careful while solving this equation. See, let's go step by step. घाई मत करो, सब मतलब अच्छे से जवाब आएगा. देखो यहाँ पे पहले क्या करना है, x of t ना, original signal produces some output. What is that? Y of t. What is that? Well, let me directly write it. X of 2t. This is what the output it produces. Let me shift the input by t naught. Shifting input. So input has been shifted. After shifting, what is it doing? It is simply scaling. But what? The independent variable. So what should I scale? Yes. So it should be x of. So when we shift the input, okay, you should be very careful after the operation. This is what you get. Now shifting the output itself. Shifting output directly. Shifting the output will result in what? By the same amount, na? T naught. क्या मिला आपको? See, what is this? Y of t minus t naught. That means every t is getting replaced by t minus t naught, not 2t. Every t is getting, so let me write that. Replace every t by minus t. That is true only while shifting the output, because we are directly making change in the independent variable of the output. So what it will be? X of बोलो 2 of in bracket t को change हुआ ना, t minus t naught. Every t is getting replaced by t minus t naught. So are they two the same? In fact, this is x of 2t minus 2t naught. Are these two the same? No, not same. Therefore, the system is time varying or it's not time invariant. Or it is time varying. Is it clear? Let's take some more examples. Solve this. Y of t, simple. Tell me. See, by visual inspection, it may appear that this system is, it's time variant or time invariant. You should follow all the steps carefully. Then only you should conclude. Okay, otherwise it will be you may land up in something very deceptive. Solve this. So it's better not to imagine and put your pen down on your copy and solve this. Step 1. You tell me. Step 1. What is step 1? First, you take the original input x of t. What it produces? X of t plus 5. Step 2. Shift the input. After shifting the input, what do we get? X of t minus, so input by t naught. What do we get? X of, now input is getting shifted, right? So x of t minus t naught, this plus remains the same, right? Step 3. Shift the output. That means what? Replace each t by t minus t naught. What do we get? Y of t minus t naught. कितना आया? So that is equal, right? That doesn't produce any output. That is equals to x of minus t naught plus 4. Are they two the same? Yes. So this system is time, bolo, take another example. We'll take a lot of examples. No, don't worry. Take this, the example which we have seen yesterday. Calculate. Find it out. Yes. Outer box represent? No. Simple bracket. Simple bracket. Unless and otherwise specified, consider it as simple bracket. Yes, time. Okay, because see, then you should see that what is making it time invariant and what is it making time varying. So when we introduce some factor of time in multiplication with this, okay, when we tweak the independent variable somehow, then it is time varying, right? So, but here we are only tweaking the amplitude, so it's a time. Tell me, time. Good. Take this. Tell me. Huh? Sure. Of course, because we are not tweaking any kind of time, so that's not an intuition. That just gives an intuition into what will happen to this system. But you should verify it with all the steps carefully. All right. So this is all about time invariant. What does it mean practically? If I am doing some experiment, if I am getting some output, the same should be true. You should get the same output. I mean, doesn't matter at what time you perform that experiment. Say for example, you perform that experiment the next day, it should still give you the same output. What will be the difference? Instead of getting the output today, we will get the output tomorrow. That's it. That's only will be the difference. Okay. So there is only a time shift which is happening in the output because we are giving the input time shift, right? So if that happens, and if that is true for all the input, for all the shifts, and for all time, then we call that as a time invariant system. Is that clear? Now let's look at some other properties. So yes.
Sir, yt equals to t plus
T plus. All right. So what? Yeah, t plus xt, or you tell me. Yes. Huh? Time varying. It should be time varying, right? Why? If you shift the input, if x of t is there, you will get y of t. Of course, if I am doing plus or multiplication, we are tweaking the time, right? Can you prove this? Take some example. Let's say you take x of t as u of t. Take x of t as u of t. Or take this example. Okay, see, let's say this is the input. Okay, u of t. Now, if you simply add in, this is u of t, right? This into this plus t, right? What is that? What is t? You tell me first. If you add them, what you will get? No, this will get up shifted by +1, right? ऐसे होगा ना, ये ऐसे ही. Okay, so this is what you will get. But what if you shift the u of t by 1? Let's say it is 1, this is u of t minus 1. That means if you shift the input x of t minus 1, what will happen? T remains the same, right? T remains the same. Add them. What will happen? Okay, from here it will be the same. From here itself it will add 1. It will be something like this. Oh, sorry, not like this. Like that. Is it okay? I'm simply adding 1 to it. Na? Here it is 1. So 1 plus 1, it will be 2 onwards, right? Now, this is what you are getting after shifting the input and testing the output. Let's shift the output itself. Let's shift this output itself. This was the output, na? Shifted by the same amount. What was that? 1, na? What you will get here, na? यहाँ पे ऐसे, ऐसे ना? Are these two the same? ये और ये? Are these two the same? No. That's why this is time varying. You got the concept? See, step 1 is to check, first check the input, let the input be as it is, check the output. Step 2, shift the input and then do the operation on the system, check the output. Step 3, shift the output itself and see how the equation looks like or the graph looks like. Compare step 2 and step 3. Are they two the same? If not, they are time varying. If yes, it is time varying. Is that clear? If you are in doubt, you draw, you try to draw this example. Okay, you try to draw it graphically. Can you do this? Can you do the same exercise for t into x of t? Please do that. For the previous example, t into x of t. Plot it graphically and prove that it's time varying. Hello? Yeah. Okay. Anything serious? Oh, it's simply a painkiller. So what I would say is, you simply take him to the Homogeneity doctor. No? That will be even better, because that there the doctor will be available. Yes, there is a doctor there available. This is a health center. Okay, there is a health center at Homogeneity. If you go to Homogeneity, they will tell you there is a health center. If you go there and report, they will diagnose it. Yeah. What about the pain? I mean, yeah, I think they have simply given painkiller. That's what I know. Yeah, I think that's right. Is the pain gone? It's still there. Okay, that means because of the painkiller that you have to get given. So better to show it to Homogeneity doctor, because that wasn't diagnosed by any doctor, right? So it will be better to show it to a doctor, safe side. Yeah. Draw this. Prove it graphically. So these things will give you more insight into the operation or the the properties of this system. Okay, try to draw it graphically. Let me see how many of you are able to do that. You can take anything. I'm just for an example. See, if I want to, again, always remember, let me write that. Let me write that. So if you want to prove certain property, that property must be proved for all inputs, for all x and for all t. But if you want to disprove anything, so we know that this is not time invariant. If you want to disprove, yes, one counter example is enough. I have given an example. If someone says that, okay, this person is always speaking truth, this is very, this is Raja Harishchandra of IIIT Nagpur. But when I see him, saying lie at least once, I will say that he is not truthful. So one counter example is enough. So if you want to disprove anything, property, one counter example is enough. Is that okay? So this you should always remember. So disproving anything is very easy. That's what I am saying. Just give one counter example. But here if you say that, okay, x of t, what should I take? Not necessarily, you can take anything. But for disproving, I have simply taken an example of u of t. You may take it constant. Prove it graphically. Is it coming the same? No. So that you can prove it. Okay, later. Let's move. Another property, fifth, is what is called as additivity. Now, see what this additivity says. Say for example, if I am having a system, okay, and if I am getting some output, if I am giving some input and that produces an output y of t, let's say some input x1t, I am getting some output y1t. If I am giving another input to the same system, assume that I am getting some output y2 of t. If I give the addition of the first two inputs, x1t plus x2t, and if I am getting the same output in addition as that of the individual outputs, that means they must be the same, y1t plus y2t. If that is the case, then we say that then the system is said to be additive. Homework for you is to plot all the signals in MATLAB. Try to plot all the signals in MATLAB and verify these properties. Alright. So what does this mean? Say for example, what should I give as an example? Say for example, you eat something and you work hard. That's the amount of energy that you have. And if you eat more, you'll have more energy, right? But that is not exactly double. Human systems are highly non-linear. But assume that you will get double the energy. If you eat double and if you are getting double the energy. So that is what it means. If you give individual inputs, say for example, if you are eating some protein bar 1, some protein bar, and suppose you are getting some energy by some company, and if you are getting another protein bar, you are getting some energy. If you eat both of them, you get both of double the energy, right? I mean, so that is what it means. If that happens, then the system is said to be additive. Okay, but these human systems are highly non-linear. So those doesn't. I mean, you can't compare this ideal systems with the human system. It can't happen. It may happen that your stomach may not accept this protein bars and you may go to washroom several times. So that may happen. So that's not additive. Okay, the system is we can't predict about the human systems. But say for example, it's an amplifier. When you don't speak anything, there is something which is called as, now you should tell me, you know everything. When I'm not speaking anything, what is the output? There is bias voltage which is there at the output. Yes, the DC biasing which is there. When we speak something, whatever the voice is, it actually rides over this DC biasing, and you will get the output. What is happening? Forget about the amplification. Assume that you are getting the same output what you are speaking. There is no amplification at the speaker. Assume that. What is happening? If you add these two signals, that output also will get added. Okay. But there is something more which amplifier does. That is nothing but scaling the input also. So it is something more than additivity that we are going to see next. But let's say for time being, let's assume that this, if this holds true, then we say that the system is additive. Okay. Let's take an example. Consider this: x of y of t equals to x of t whole square. Tell me, is this system additive? Let's go step by step. First, step 1. First give one input, x1 of t. What will you get as output? x1 of t whole square. Try to give another input, x2 of t. What you will get at the output? x2 of t whole square. Add them together and try to give them as out input. What you will get? X of t has been replaced by x1 of t plus x2 of t. So that will be simply an addition of x1 of t plus x2 of t whole square. But let's check the output. What if we add the output? y1 of t plus y2 of t. What is that? You add individual outputs. What is that? x1 of t whole square plus bolo x2 of t whole square. Are these two the same? Are these two the same? No. What factor is it introducing to make this as non-additive? Yes, very good. So this, whenever there is a non-linear operation, now it should give some hint to you. Whenever there is non-linear operation involved, the system should be non-additive. Okay. So let me write on a fresh page. So what I'm saying is, if you take individual inputs, x1 of t plus x2 of t, that will give you an output of x1 of t plus x2 of t whole square. This is when inputs are added and given to the system. But when we add the outputs themselves, we expect them to be the same, right? If we add individual outputs, so y1 of t plus y2 of t, what you will get? x1 of t whole square plus x2 of t whole square, and this is when individual inputs are added, right? Outputs are added. Are these two the same? No. So this is what is equal to x1 of t whole square plus x2 of t whole square plus twice of x1t x2t. So it is this factor which is not allowing the system to be additive. Is that clear? Is that clear? So this system is not additive. Take another example. Y of t take this, solve quick. Yes, tell me, quick, solve, don't prompt, solve by yourself. Add the individual inputs, check the output. Add individual outputs, check what it is. When solving this, you should be very, very confident. Okay, otherwise, you know, ये ऐसा होगा क्या, वैसा होगा क्या. See, these things will work on with practice. Okay, you must practice. आप 10 किताब कम पढ़ो, पर एक प्रॉब्लम सॉल्व करो. That will give you confidence. Okay? This is not additive, right? It's not additive because this 5 factor gets added only once. Okay, when you, so this is not additive. How will you prove that? X1 of t, if you give, will get y1 of t, that is nothing but x1 of t plus 5. If you give x2 of t, will get x2 of t plus 5. When we add them together, y1 of t plus y2 of t, or first let's add the inputs, x1 of t okay, this is going down. x1 of t plus x2 of t plus 5, which is not equals to y1 of t plus y2 of t, right? What is that? x1 of t plus x2 of t plus 10. Okay, all right. Next, another property which we are going to see is sixth one, right? It's very, very important. It's called as homogeneity or scaling. What does it say? Say for example, I'm having some input and it produces some output y of t. If I scale the input by some factor c, some constant, I should get the same output, just the scaled version of the same constant. Oh yes, C of I. What does it mean? Say for example, I am speaking at some pace or some amplitude. I am getting some output at the speaker. If I speak loudly, it will be louder in the speaker itself. So it should be the same scaling factor by which I am scaling the input. All right. So if that is true, if this is true, then the system is said to be homogeneous or follow scaling property, homogeneous. Well, now this should be true for all inputs for all values of C, and it must be the same C. It may happen that it is getting scaled by 1 or sorry, let's say example 2, but at the output it may get scaled by 4. That's not allowed. It must be the same. So for all C, X and T. Well, the point to note is C may be anything. See, what we have seen is time is usually real number. Okay, I mean we assume it's of course real, but in general we allow this input signals or constants even. So I mean the dependent variable to be complex in general. Okay, what I'm saying is, although the independent variable we allow them to be real values, but dependent variable and constants this is very important, dependent variables and constants, in general we allow them to be complex. See, no one stops us in having that those independent variables as complex. I may have system, let's say j into x of t. I may have that kind of system. Okay, so output in general is a complex. So dependent variable in general may be a complex value. So let's consider this system. Example. Consider the same system which we have seen just now. X of t. Go step by step. Go step by step. Step 1. What is step 1? First check the normal input. Normal input का output क्या आएगा? X of t whole square. Then you scale the input. Okay, scale the input. C x of t. What is the output? मतलब x of t is being replaced by c into x of t, right? So how much is that? C square x of t का square, both का square, right? Then so this is what? Scaling the input. This is step 1, step 2, step 3. What is step 3? Yeah, scale the output. What if we scale the output? C into y of t. What would be? Equals to, बोलो क्या है? C into, yes, C into x of t whole square. Are these two the same? So this is what? Scaling the output. Yes, scaling the output. So are these two the same? No. So 2 is not equals to 3. I mean step. Okay. So this is not homogeneous. Is that clear? Take another system. Example. Y of t x of t plus 5. Same example. Tell me quick. Quick. Another example. Yeah. Can you tell me about this? Yes. So now you got the idea, right? I mean, when you scale the input and when you directly scale the output. Okay. Are you getting there? Understanding the things? Is that clear? Everything is fine? Now take this as an example. Take this as a homework. Y of t square. Now if I do any variation, you should be able to understand these things, right? So you may tell the systems are now okay. Homework for you is like, we have seen all these properties, right? So come up with examples with all sorts of systems. Some systems may be homogeneous, may not be additive. Some systems may be additive but not be homogeneous. Some may be memoryless but may be causal, and so on, right? So come up with all such examples, lots and lots of examples of all the possible combinations of the system properties. Okay, that will give you a good brainstorming, and that will very well.